This is a project that's really just started, so it's at the complete other end of the spectrum. We've only been at this, it's 7 or 8 weeks now. Dave Picard was the key person in getting this off the ground, and David Tyner prepared most of these slides. He's a postdoctoral fellow working with me that Dave is helping guide through this project. And what this is in a response to a RFP issued to take a look at air emissions associated with unconventional gas exploration and production. So the objective, quoting from the RFP, was to provide a broad overview of the atmospheric emissions associated with hydraulic well fracturing in the upstream oil and gas industry in Western Canada. It's a bit of a tall order. Participants are Carleton University and Clearstone Engineering, and it's, I don't want to say it's a small project, but it's a big project in time, but it's a modestly funded project, and Felice Onder in Canada is the project champion. So the specific tasks we're trying to look into are a literature review, which most projects start with some kind of a literature review. This one is quite different in the sense that usually you say literature review, and that's something you do in a kind of a week or so. I think literature review is going to be one of the main deliverables of this. This is really a challenging area to sort out the noise from the signal. From that, we're going to look to compile reported venting and flaring data for drilling and completion activities, and that's to come. We're trying to arrange, and Felice is very helpful so far, interviews with industry to help get a supplement things we're looking at in item 2, data analysis, and then report preparation. So really we're in step 1, and we're not even done that here, but I thought, well, Lori wrote it on the agenda, so I figured we better talk about it. So, what I'm talking about really are just some very preliminary, maybe the results is a bit strong, but just to give you a sense of where we're starting. So, terminology. First thing you hit is that unconventional gas means a lot of different things to a lot of different people. In fact, I was reading last night in the 3 hours waiting for the plane to take off, EPA has just recently decided they're going to drop the term. They're not going to use unconventional gas anymore because it just doesn't mean anything anymore. They're going to talk about hydraulic fracturing exclusively, be it for shale, tight gas, or coal bed methane. Tight gas and coal bed wells are typically vertical, and I'll show you why I can make that claim. Shale gas wells are typically horizontal, so maybe that's a useful distinction. API, American Natural Gas Association, have just, in response to some EPA emission factors, published survey results that are quite interesting, quite enlightening in a number of fronts. They're criticized in a number of fronts, but there's a lot of very useful information there. And so here, for example, surveying the industry for 2010 and first half of 2011, number of completions categorized as conventional shale, tight, and coal bed. You can see that 84% of shale gas are horizontal wells with hydrofracturing, so that kind of supports the generic description. But one of the things you see when you start trying to wade through the literature is different people mix these things up different ways, and it's really quite confusing. Things you probably know, estimated marketable Canadian resources are in the trillions and trillions of cubic feet. Horn River Basin in BC is already a big player in Montney gas plays. Significant coal bed methane in Alberta, but there's potential shale resources in significant potential resources in other parts of the country. Other parts of Alberta, Quebec is sitting on a lot of potential resource in Brunswick, and I'm not sure they've fully explored east of that. Shale gas, 2035, production increase going up to 4 billion cubic feet per day, 22% of total natural gas production. This is now using how the National Energy Board defines shale gas and tight gas, but tight gas then makes 49%, so together that's 3/4, just those two from the National Energy Board. And so really the title is correct. The unconventional gas, if you include all of these things, is the new norm moving forward. So this is where things are going in gas. So Let me do my version of Shale Gas 101 on how this process works. And that's, I think we're just talking about this as I talk very briefly about where the emission sources might be coming from and the challenges we're going to face. So, as with any process, you have a drilling and casing insertion step, and that's the iterative step. You drill, insert some casing, and away you go. But once you've got your well drilled, first thing you're going to perforate the casing section. Then you're going to do hydraulic fracturing, and so that's to free up formations. You're going to have some kind of flowback period where you're bringing that fracking fluid out, whatever fluids come up from formation. But there's also gas that is released during the flowback. So that's one of the key processes that's very difficult to get a handle on and swings the different studies a lot of different ways. Depending on what you're doing, you're going to do a multi-stage frac, put a flow plug in of some kind, do the casing perforation again, frac that section, and do that a few times. Now you've got these flow plugs in, and there's different types of flow plugs. It depends on the type of flow plug you do. That also affects the emission rates, whether or not they're cemented off or if they have flow-through valves. There's some drill-out step. There's another flow-back stage, and then finally you're into production. It's pretty nice and simple. Even as complex as that is, it's nice and simple when it's a cartoon. The reality, of course, is probably nothing like the cartoon. And so if you're going to try to get a handle on the emissions, this is, again, a very simplified block diagram of the things you might want to consider. During the drilling and casing insertion, there's some amount of venting that may or may not be flared. Perforation, hydraulic fracturing, the flowback is another significant section. Drill out and then flowback again. There's significant, there are important steps anyway. The numbers may or may not be significant, but there are important steps to consider correctly if you're going to get a useful, applicable emission. And at that point, you've completed your well and you go into production. But during production, depending on the formation, you may need to do liquid unloading. It seems to be common in some basins in the States. I honestly don't know how relevant that is here at the moment. You may do recompletions or workovers, and the rates you do those things are very important things to factor in. The well production, how you handle your condensate, and is that in the sorts of tank stays measuring, and the emissions vented or flared, that's an important consideration. And then whatever on-site gas processing you may or may not have are potential sources that may or may not be considered. And that gets you the sales line. And then depending on your study and what you're doing, you then may or may not want to consider emissions downstream from that as you go through the pipeline distribution network and compressors and whatnot. You may go all the way to the end and say, what do you use the gas for? And do you generate electricity? And do you do it on a gigawatt of electricity basis or a thermal basis? And the reason for dragging you through this is if you're going to try to make sense of the literature, you kind of have to have some appreciation that all these steps were either directly considered or indirectly considered by being neglected in the various studies that are out there. And once you start looking a little more physically into what's going on, you start to appreciate why there are these vastly different numbers and why maybe you don't need to put a whole lot of stock in any of them at the moment. So, emissions from unconventional gas, I think it's fair to say there's a critical lack of comprehensive sources of emission data for unconventional gas production. That's not a surprise, I don't think, to anybody. There's much debate over the quality, objectivity, representativeness. I'm not sure if that's even a word, but if you know what I mean, completeness and accuracy of available sources. And so a lot of that complaints or those big long adjectives go to data that's collected by the EPA. Most current studies in some way point back to data derived by the US EPA through the STAR program workshops. And I'll show you another slide in a minute. More recently, there's this survey data, operational survey data from API ANGA that has the potential to significantly change how we interpret that EPA data, I think mostly for the better. But one of the things looking at for directly relevant, openly derived data from Canadian basins is lacking. I think that's one of the reasons looking at this RFP is to try to see if we can look into that a little better. So I guess I could reorder this a little bit, but I'm operating under the premise that most people have heard of unconventional gas, and most people have heard of various studies that go from things like this really is a great, wonderful, clean energy source for the future, to this is worse than coal, and numbers in the middle. My goal talking today is not to get into the details of any of those particular studies, but to show what's the difficulty in getting a reasonable measurement and how we're going to start to look at that at this stage of the study. But to give some context, I think it's useful to take a look at the EPA numbers, because most studies in some way point back to here. EPA in 1996 had these emission factors. And these are some of the major processes that were in those nice little cartoons I showed you. Liquid unloading, well completion, workovers, wet seal compressors were a big source in their revised standards. In 2010, EPA updated these emission factors, and things that were 52 for liquid unloading went to factor of 10 up 570. Well completions, numbers like 1 went to 36 and almost 10,000, or 9,100. And wet seals that weren't considered at all, numbers like 12,000 and millions of cubic feet methane per year per well. And so you can see these are just the numbers as they are. Not getting into whether or not these are believable at the moment. That'll come up in a second. But this is why things are as they are now, in a sense that suddenly in 2010 these numbers were changed, and they were really changed. They weren't changed a little, they were changed a lot. And if you do studies based on these numbers, you get widely different conclusions than you had before. And so I think if anything, some of the more quoted studies have helped focus attention that this is an important thing that needs to be looked into. And really in direct response to that, API, ANGA, one of the first things they did, this is all happening very fast. This is another challenge doing this as a lit review. There is literally, what I've used word, but I mean it literally, there are literally new studies every week. And since we've started, there's been significant developments and things that we've added to the list. We're at over 100 sources so far, and it's not closing yet, which is a little frightening. It's a good thing we work at a university, so we don't have to make money doing this stuff. It's just for interest, and it's a great problem. So in response to the EPA emission factors, API, ANGA did really quite an impressively comprehensive survey. Now there's some criticisms for how they designed that survey. I think it's fair to just acknowledge that there are criticisms, so I'm not saying that these are the answers, but at the end of the day, there's better data here than there is available in a lot of other sources. The survey based on 91,000 wells, approximately 26% of the US EPA well inventory were actually surveyed, covered 19 to 21 of the basins, American Association of Petroleum Geologists basins. EPA data is derived from 8,800 wells, not small, but different order of magnitude. And what they were trying to get at was liquid unloading, well completion, well recompletion rates, because these are so important in that block diagram I was showing you for driving the emissions. I showed you the EPA numbers. Really, this isn't supposed to be a talk about numbers. I just want to contrast that with things that are in the API ANGA survey results. They found things like 45% of unconventional wells surveyed at plunger lifts. Put a plunger lift in, that significantly reduces the emissions you get during liquid unloading. That wasn't considered in the EPA numbers. So there's good reasons for large differences here. Still 11%, 16% of unconventional wells they found were directly venting, this API data. Their emission factor is a number like 175 million standard cubic feet methane per well. If you took their data with the EPA assumptions, that would have been 1,300. And so API's contention that, I think on balance of probability is probably the most correct, is that 1,300 really should be more like a 175. Probably there's an answer in between, but that's an example of things that really swing the numbers a lot. Well completion data, unfortunately, the API ANG data was insufficient, or they deemed it insufficient to provide emission factors for flowback. So no matter what, our interpretation of the data review so far is that still we don't have reliable sources that are going to get us concrete, definitive answers. So there's definitely shortcomings still. 1.6% fracture wells required workovers, EPA at a number like 10%. That really changes things. And their data suggests 72% lower methane emissions due to workovers, and et cetera. So there's really two quite different points of view. So those, there are some other sources of data, but those are kind of the main ones. And I guess really I'm trying to set the stage a bit. With that backdrop, then you start to take a look, just very briefly, at some of the life cycle studies that are out there. So I want to just take a couple minutes to talk about that. And when you start to look at these different things, the Haworth study at Cornell was the first one and the most quoted one. That's the one that says, unconventional natural gas is, well, it says a lot of things, but the thing that gets quoted is the numbers on a 20-year time scale suggests that overall greenhouse gas emissions are worse than coal. A number of other studies since have refuted that. But when you start to look at the nitty-gritty of these different studies, you find that the definitions of unconventional wells right off the top gets mixed. So it gets very hard to compare them at the outset. As I mentioned, EPA has dropped the use of the word unconventional in their this year's inventory. It's the first time I heard that. Different studies consider different geological areas, and there's ample data to suggest that different geological areas have different behaviors, especially when it comes to things like liquid unloading. And different studies do or do not include that, and that single thing can drive the emissions factors of 2. GHG footprint measurement, a lot of debate. The Cornell study did it per unit of energy, other studies do it per unit of electricity. You get significant differences when you do that. And part of that's doing the energy conversion. So this, I don't want to dwell on this, but this just compares several of the main ones. So Cornell, NATL, which a lot of people saw as a direct rebuttal of the Cornell study. Carleton University, S&T Consultants, Enercan, there's a Deutsche Bank, and a Tyndall Center. Those are some of the main ones quoted. Other things that swing the numbers depends on what time scale you consider, 20-year, 100-year. Cornell used numbers from Schindel and Nature that are more recent than the IPCC is their argument. Others would counter and say that those aren't internationally recognized at this stage. I'm pointing that out as a difference at this stage. Other studies have used Kyoto numbers of 21 that are, most people would say, are quite out of date. Did you do it per chemical energy or unit of electricity? And big numbers. This study, I believe, tried to do Monte Carlo analysis. So they basically said, look, all these things are really uncertain. We really don't know a lot of these emission factors. And they said, well, plus or minus 40%. It could be 40% better, or it could be 40% worse. And if there's a takeaway from here, I personally, at this stage, I don't want to prejudge, but I'm not putting a lot of stock in any of these numbers myself. This is the one if I want to pick one to believe, I'll probably pick that one at this stage, and that, I don't know what it is, it's plus or minus 40%. It's really difficult to sort these things out, and that's kind of that is what we're foolishly have agreed to try to look into. So, getting answers. How are we going to get through this? Yeah, thanks, Randy. Rescue me. We need a clear need for objective technical analysis, and that's the motivation for the RFP. And I think PTAC and CAP deserve credit again for bringing these forward. Data availability is a critical challenge. I mean, some of this data isn't there. There is a study I'm aware of that it's a collaboration between industry and the Environmental Defense Fund in the US that they're currently attempting to measure emissions during well completion events, but it's completely locked down in confidentiality, but that data may appear, to my understanding, in the new year. So that's likely to change things again. Different engineering question. But another thing to keep in mind is different engineering questions warrant different assumptions. So try to avoid directly criticizing any one study because it depends on what you're asking, what sort of frameworks you might want to look into. The challenge is to wade through the myriad sources. So if we are to do this, or someone wants to do this, this is really the kind of thing I want to bring forward, and then I'll end with these kind of 6 points. If you're really trying to get accurate, defensible, peer-reviewable kind of data, by our estimation at this stage, these are the sorts of things you need. First is you need geographically diverse data. Different plays have quite different characteristics, and that really matters. And that's generally quite overlooked in the sort of life cycle studies that are out there. Range of operating practices, just examples, CO2 content can swing things a fair bit when you start looking at the methane emission factors. And there's examples from basins in Canada that vary a fair bit, 1 to 12%. If you're trying to get at combustion emissions, you really need to understand all the combustion emission sources, and they can be significant. There's a lot of energy involved in this. So you need access to data that's not always easily attainable. And so when some of these life cycle studies start to diverge, a lot of it comes down to how they dealt with these necessary assumptions. Maybe they made good ones, maybe they didn't, but it's difficult. On-site equipment, benching emissions, dehydrators, how you handle that. Liquid unloading emissions are a really key one that have been overlooked in a number of studies. What are the use rates of mechanical lifts, well blowdowns, which formations need unloading, etc. Well completion emissions, number of completed wells per pad, fracturing stages, how often are you using reduced emission completion, or so-called green completions. Well servicing, workover rates are very important. They can really swing the numbers. And one of the most sensitive, but unfortunately most critical, is well lifetime data. This is typically gets to proprietary things, so people don't want to release their estimated ultimate recoveries. But it's been shown in an interesting paper by Hughes, last thought I'll leave you, just to how difficult this can be if you don't have good data going in. The results at Cornell that are so out there on one end, and the results of the NATL survey that are somewhat on the other end, those can be brought together, changing just the estimated ultimate recovery. And so I guess where I leave is, this is a very important challenge. I think probably most people here would agree, but it's quite a daunting one, and moving this forward is going to require quite a bit of work and quite a bit of data collection. And I'm happy to have the support of people here, and Felice especially for getting us going, and Dave. And